Hey, this is your stats sensei, Mr. Spensei, and we're here to talk about power, error, and tests. And we're going to look at a uh, free response question that came from a 2018 question 6. All right, pretty good question. So systolic blood pressure is the amount of pressure that the blood exerts on blood vessels while the heart is beating. The mean systolic pressure for people in the United States is reported to be 122. So we have a population mean of 122 and with a standard deviation of 15. Now notice we have the standard deviation of the population. So if we're running any sort of test, this is going to be a z-test running for normal. So the wellness department of a large corporation is investigating whether the mean systolic pressure of its employees is greater than the national mean. So here we have looking for a greater than the national mean. A random sample of 100, so we have a sample size of 100 employees will be selected. The systolic blood pressure of each employee in the sample will be measured and the sample mean will be calculated. Let mu represent the mean systolic blood pressure of all employees of the corporation. Notice this is of the corporation. This is not of the US. So this is the mean of the corporation. We know that this is the mean of the population. We want to know if the mean of the corporation is equal to that of the population of the US or whether the mean of the corporation is greater than the mean of the US. The first off is our first error is describe a type 2 error in the context of this problem. Please remember when we're talking about errors, the very first thing you should do is give the definition to let the grader know what you're talking about. So a type 2 error occurs when we fail to reject a false null hypothesis. That's a definition. That's all well and good, but that will get you no points, but it lets the grader know that you know something about errors. Now we need to put this in context of the problem and go like this. In the case, the wellness department would believe that the mean systolic blood pressure of its employees was no greater than the mean systolic blood pressure for the population of the US, when in fact, the employee's mean systolic blood pressure was greater. All right, so basically we're saying this is what we believed, it was this is an error, this is what the actual truth is. All right, this kind of follows our template that we rolled out earlier when we were rolling out the simplified recipe card. So I look at that simplified recipe that we used in a previous video. All right. So assume that the standard deviation of the systolic blood pressure of all employees at the corporation is 15 milligram. So the standard deviation of the employees is 15. If mu equals 22, the sampling distribution of X bar for samples of size 100 is approximately normal with a mean of 122 and the standard deviation of 0.5. What values of the sample mean X bar represent sufficient evidence to reject the null at a significance level of 0.05? So here's what they're saying. All right, let's just say that we have a mean equal to 122. All right, we're looking for an X bar that we're going to reject, and our rejection zone is based on an alpha of 0.05. So I need to find, not only do I need to find this X bar, I need to find associated z-scores. Well, this is the associated z-score with the mean is always 0. So I need to find this missing z-score right here. Well, to find that missing z-score, I'm going to use the second var's inverse norm function on the calculator. So second var's, oops, let me turn this thing on. Here we go. Second var's inverse norm. And my area is going to be 1 minus 0.05. My mean for a z-score is 0. And my standard deviation of a z-score is 1. And I end up getting a z-score of 1.645. So that's my z-score, 1.645. Well, I want the probability that 1.645 is we're looking to be greater than, moving more extreme, than X bar minus 122, 15 divided by the square root of 100. So we're going to simplify this down because we're going to have to solve this by algebra. So this is going to be 1.645 is greater than x bar minus 122 over 15 divided by the square root of 10, which can be, by 10, 15 divided by 10, square root of 100 being 10. We'll simplify it down one more step. 1.645 is greater than x bar minus 122 over 1.5. At this point, I can go ahead and break the calculator out. I'm going to multiply 1.645 times 1.5. And then I'm going to add the 122. And I end up getting 124.467. All right. So this right here would be the x bar that we were looking for. I should note this is my x bar of 124.46. And my z-score that was associated with that is the 1.645. All right. So the next page, because it's a question 6, so you know it's going to be long. So the actual mean systolic blood pressure of all employees at the corporation is 125. So this is the true population mean for the employees, not the hypothesized 122. Using the actual mean of 125 and the results from part B, what did we get in part B? We got a rejection of 124, or an x bar of 124. Determine the probability the null hypothesis will be rejected. All right. So we want to figure the probability that we will be rejecting. All right. So with that said, our true population mean happens to be 125. That's the true population. We want to know the probability that we're going to get a sample of the 124.46. Well, we can see that this is going to be greater than 0.5. All right. So z equals x bar minus mu sigma divided by the square root of 1, square root of n. So that's a probability. There's my x bar. That's what came from the sample. This is the actual true population mean. Our standard deviation was given to us in the previous part, and it was a standard deviation of the population being 15, and our sample size is 100. So probably the easiest thing to do is go to stat test and press z test. And our mean was 125. Our standard deviation for the population is 15. Our x bar 124.4675, and our sample size of 100. And we're shading off to the right. Just remember, this goes off to infinity. And when we do that, we end up getting this area being 0.6387. So in this case, the probability that we'd actually reject the initial claim of 122, because that was our initial claim, the probability that we would reject that in favor of an alternative is pretty high. It's 0.638, and it's high because the true population mean, the actual population, is 125. It's not the hypothesized 122. So the probability of correctly rejecting is 0.6387. And those words that I just said, 0.6 probability of correctly rejecting, ties us to part D. And it says, what is the statistical term used for the probability found in part C? Well, the probability of correctly rejecting. Well, the probability of correctly rejecting happens to be power of the test. Because the true population mean is 125, we should reject the null. The probability of correctly rejecting the null is power. All right, so that takes care of part D. Finally, part E, and they were very picky on this. I think they went a little bit overboard on their grading, but it is what it is. We don't get to question the master. All right, suppose the size of the sample of employees is to be selected is greater than 100. Would the probability of rejecting the null be greater than, less than, or equal to part B or part C? Well, they said we're going with greater than 100. So we're going to increase our sample size. Well, increasing sample size increases power. All right. So an increase in sample size would increase the power of the test. This is because the standard deviation of X bar, by the way, we have to back it up with a reason. And it's the reason is the standard deviation, because the standard deviation of X bar, which is sigma divided by the square root of n, will be decreased as n increases. So as this number gets bigger in the denominator, as this gets bigger, this should be the standard deviation of X bar, excuse me. This should be standard deviation of X bar. As the standard deviation of X bar will increase as n gets bigger, because we're dividing by a bigger and bigger number. Now, you also had to have this part, and this is where I disagreed with them. I disagreed that we needed to include it, but nonetheless, we needed to say so. They said so. So we had essentially, this is our initial formula. So z equals X bar minus mu sigma divided by the square root of n. Well, all right, as this part gets bigger, or as n gets larger, a smaller sample mean would be required to reject the null. So as n gets bigger, a smaller sample mean is required to reject the null, which means as n gets bigger, it's easier to reject the null if the null is false. I'm going to say that again. That's pretty big words. If as the sample size gets bigger, we need a smaller and smaller mean to reject the null if the actual null is false. So increasing the sample size makes it easier and easier to reject a false null because we minimize the amount of sample variation. All right, sayonara. Thanks for listening.